I got my hands on these sensors. These are mainly IMUs that contain triaxial accelerometers and gyroscopes. But there are also magnetometers in these boards, and pressure sensors that I'm not using at the moment. Here there is also a humidity sensor that I don't plan to use in the near future. So I started working on orientation estimation algorithms, and I made some dead reckoning experiments. I learned that one cannot estimate the position using only IMUs, but I wanted to know how much we can improve our estimations with a proper calibration. I made some research on the current state-of-the-art literature on triaxial sensor calibration. I learned that the measurements of these things can depend on their temperature, and I designed some hardware. This thing was the first one. It helped me to collect calibration data, which I used to test my calibration algorithms. But it was not the last one. I designed more hardware, and after some versions I arrived at this one. We are watching now a calibration routine. This takes like an hour, so I will speed up and pause in some parts to give some details. The first thing to notice is that there are two sensors here, each one connected to an Arduino. The Arduino is requesting measurements, and once received, they are sent to a Raspberry Pi that is placed here at the back. The measurements are stored in the Pi memory for later calibration. You probably have noticed that the gimbal is moved by two servos. One of them is here. You cannot see the other one, but is placed inside here. Both are controlled through the GPIO pins of the Pi. I had to include some gears because the servos only rotated 180 degrees, and it was necessary for this servo to perform a full rotation. I also included these guides to keep the gear from getting out of place. There is also a stepper motor down here. We use that to provide an angular velocity to the gimbal. Here, at the left, there is a Peltier device sandwiched between two heat sinks. We use that to heat and cool the sensors, so that we can obtain a temperature-dependent calibration. I did not say that before, but the whole thing is inside a temperature-insulating chamber made from an icebox. Both the stepper motor and the Peltier device are controlled by this other Arduino that receives requests from the Pi through the Bluetooth. Okay, so now you will see a fast-forward video of the process of capturing calibration data, and at the end I will show you the result. This is the file that contains the calibration data, and this is an example of a calibration that results from applying the calibration algorithm. Now, this is a demonstration of how the calibration of the IMUs influences the performance in dead reckoning. We have here 5 IMUs, 4 of them mounted on this protoboard, and the other one is connected to the Pi. I am estimating the position of each sensor independently. The relative position between sensors is not estimated. The position and velocity is reset each 5 seconds. Each color represents a different sensor. Estimations made with non-calibrated sensors are represented with darker colors. Now I'm going to move the set of sensors, and I will let you judge the differences between calibrated and non-calibrated IMUs. I think there could still be room for improvement with a better calibration system. Okay, this is the end, but you can check the video description for more information. Thank you for watching.